A plane is flying 800 kilometers per hour south with no wind. Over a short period of time, a strong wind develops with a speed of 120 kilometers per hour in the west direction, causing the plane to drift off course. Assuming the pilot doesn't make any changes, what is the new speed of the plane over ground, and what is the angle between the plane's original direction and its new direction due to the wind? Alright, there's a lot of information there. Let's read it again and pick out what's important. A plane is flying 800 kilometers per hour south, with no wind. So we have a plane with a velocity vector, and the plane has that velocity without any wind. Over a short period of time, a strong wind develops with a speed of 120 kilometers per hour in the west direction. So now we also have some wind which has its own velocity vector of 120 kilometers per hour west. This causes the plane to drift off course, so the direction of its motion changes. The pilot doesn't make any changes, which means the plane doesn't speed up or slow down, and it doesn't turn to compensate for the wind or anything like that. The problem is asking us to find the new speed of the plane over ground and the angle between the plane's original direction and its new direction. So if we're looking for the new speed of the plane and its new angle, that means we're looking for the magnitude and angle of the plane's new velocity vector. Let's draw some things to help us solve this. First, we're dealing with compass directions, so let's draw those for reference. The plane starts with a velocity vector of 800 kilometers per hour south, so let's draw that and label it as VI for the initial velocity of the plane. Then, later on, we have some wind with a velocity of 120 kilometers per hour west. The plane is still flying 800 kilometers per hour south through the air, but the air happens to be moving west at 120 kilometers per hour. So, relative to the ground, the plane has a new velocity vector, which is its original velocity vector plus the velocity vector of the wind. Let's label this new velocity as VF for final velocity. This is like a boat pointing straight across a river, but there's current pushing the boat sideways, so the boat moves at an angle. Don't worry if this scenario isn't intuitive. It should make more sense after practicing these types of problems, and we'll explain this stuff more in the lesson on relative motion. But for this problem, we want to find the magnitude of VF and its angle relative to VI, the original velocity vector. For the given information, we can write down that for the plane, VI is 800 kilometers per hour south, and for the wind, its velocity is 120 kilometers per hour west. But like last time, it might just be easier to label the pictures. And we're trying to find VF, the magnitude of the new velocity vector, and theta, the angle between VF and VI. So we're adding two vectors, but since they're perpendicular to each other, they already form the components of the resultant velocity vector. So all we need to do is find the magnitude and angle of the new vector, and we can use these equations. First, let's find the magnitude. If we rearrange the Pythagorean theorem equation, the magnitude of VF is the hypotenuse, C, and A and B are the legs of the triangle, which would be 800 kilometers per hour and 120 kilometers per hour. When we calculate that, we get 809 kilometers per hour for the magnitude of VF. Now let's find this angle. In this case, the opposite side from the angle is 120 kilometers per hour, and the adjacent side is 800 kilometers per hour. When we plug those in, we get 8.5 degrees for theta. So the new speed of the plane over ground is 809 kilometers per hour, and the angle between the plane's original direction and its new direction is 8.5 degrees. For this problem, we used compass directions, and we didn't use the x and y axes. We added one-dimensional vectors and found a reference angle. But if the problem was asking us to add two-dimensional vectors, like in the first problem, then we would have to keep track of positive and negative components, and in that case, it might make sense to use the x and y directions to keep track of things.